Okay, so let me introduce the second speaker today. It's Aline Andrade from the Universidade Federal de Minas Gerais, and she's going to talk on rank 3 instanton bundles on P3. So please, Aline.
Thank you so much. First of all, I would like to thank the organizers for the invitation. It's a pleasure for me to be here. Well, I will talk today with this joint work with my Sergipanos friends, Danilo Santiago from Instituto Federal de Sergipe, Danilo Silva from Universidade Federal do Sergipe, and Luis Carlos Sobral, which is a former student from UNICAMP. So, first of all, I would like to talk a little bit about instantons, so I can show you why this is interesting, at least for me, okay? So, the instantons, or the pseudo-particle solutions of the classical Yang-Mills solutions are for grand interest for physicians and mathematicians since the 1970s. So, from the physicians, it's obvious the importance. So, for us, the stars begin in 1978 with this relation with the solutions and holomorphic vector bundles on P3, okay? So, this connection was later expanded to a little bit more. We have not only the definition of instance for P3, but for other odd-dimensional spaces, okay? And these ones was what I call the mathematical instanton bundles. They were rank 2n vector bundles on P2n plus 1. So the rank is one unity lower than the dimension of the projective space. And in order to try to understand a little bit more of these, the importance and of these vector bundles, in 2005, Jardim expands the definition and to even dimensional spaces, and also gave these cohomological conditions or characterization that expands not only to vector bundles, but the definition of torsion-free current shifts that we call instanton bundles. This is the definition that I like because it involves cohomological conditions. And what we call the instanton shifts now this way. So, I'm sorry. Yes. So, an instanton shift on Pn for n greater than equal to, so not only P3, so for every n-dimensional space greater than equal to, is a torsion current shift on Pn with the first Chern class equals to 0 that satisfies these homological conditions. So this one is always valid, this one just for n greater than equal 3, and this one for n, oh my god. This one for n greater than equal 4, okay? So this integer over here, this Chern class, not this other characteristic, is the charge of E, which is the same as the charge for the physicians. So, okay, but what's the relation of these guys, of these torsion-free current shifts, with the ones from the beginning? First of all, when we consider E locally free, it's in fact an instanton bundle. And when E is a rank 2n bundle on P2n plus 1, this is it has trivial splitting type. This is the exactly ones from the definitions of Okonecki splinter. Okay? Well, even in the 70s, the physicians made this conjecture that the modular space for these vector bundles on P3 for rank 2, they was smooth and reducible and has the expected dimension, okay? So the goal for the mathematicians was try to prove that this conjecture was right. So in 2003, Coanda, Tikhonov, and Trautmann, they proved that the moduli space for rank 2 instanton bundles on P3 was in fact irreducible and smooth, and this proof unified all the previous proofs from C, the charge, lower or equal 4, okay? So, as you can see, this problem started in 1978, and this proof was made in 2003. And in 2012 and 2013, Tikhonov proved the, oh, I'm sorry, I will try not to do this very often. And in 2012 and 2013, Tikhonov proved the proved the irreducibility of this space for arbitrary charge. Okay, has these two papers because he has to split into cases, an even charge and odd charge. Okay, and finally, the smoothness was proved in 2013 for Marco Jardim and Repitsky. Okay, well, so the problem is over. We have nothing to do here. No. Between this 978 and this deck that's over here, a lot has been made in order to try to prove this. So it was very hard to do this. So we have to add some conditions and talk a little bit more of these instances. First of all, in the first generalization of O'Connor-Spindler, they first assumed that this mathematical instanton bundle is supposed to be symplectic. What that means, when we're talking about the bundles, not of the current sheaves, these bundles are what we call autodual. So they are isomorphic to its dual. And when this isomorphism is schill-symmetric, we say that E is symplectic. And when phi is schill-symmetric, and when we say that E is orthogonal, when phi is symmetric. Okay? So the seventh, they assume that this mathematical instanton bundle is supposed to be symplectic. Okay? It was a imposed condition. But then in order to study these moduli spaces, but then we discovered that this is not a necessary condition to be imposed. I will talk a little bit more. First, in 2002, Laura Costa and Ottaviani proved that the moduli space of the symplectic instanton bundles over P2n plus 1 is affine. So they proved that it was affine even before that they proved that it's reducible in this smoothness. And Bruto, Markuchevich, and Tikhonov identify irreducible components of the expected dimension of the modular space of symplectic instanton bundles on P3. I like very much of this paper because it's the one that gives the idea of my PhD thesis on instantons. In order to study these irreducible components, they associated the symplectic instanton bundles with schill-symmetric matrix forms, and then I studied the orthogonal case associating them with symmetric matrix. So I like very much this paper. And in 95, Miranda and Aurus Lacourt, they prove that this modular space is singular for n greater than 2 and charge greater than 3. So as you can see on P3 is smooth, but for P5 and then on, it's not. Well, Laura Costa, Hoffman, Miroyd, and Schmidt proved that this modular space of all symplectic instanton bundles is reducible for n greater than 2. Okay? So this is some of the results that was made in order to see a little bit more and understand a little bit more of these instantons. And when we are trying to, but they all, as you can see, related to the symplectic case. Because when we are trying to study the orthogonal case, what happens is in 2009, it was proved that there are no orthogonal instanton bundles of rank 2n on P2n plus 1. So, as I recall, let me recall. We start on rank 2 on P3, okay? So they prove that the first generalization, which means for the mathematical instanton bundles, there are no orthogonal bundles with this orthogonal structure over here. Okay? So was the first thinking. And then in 2016, Jardim, Marchesi, and Wisdorf, they proved that there are no orthogonal instanton bundles are trivial space in type and arbitrary rank on second Chern class equals to 2 or odd on Pn. So until this day, in 2009 until 2016, that we only have results of no existence of orthogonal instanton bundles. So with the help that the paper that I already mentioned, what we have done in 2019 was to associate these orthogonal instanton bundles with symmetric matrix. So we are able to prove the existence and build explicit examples of orthogonal instanton bundles on Pn. And also we have for charge greater than or equal to, we had a bound for the rank of these bundles. And more, when we reach the upper bound, we are able to prove that the modular space of these orthogonal instanton bundles in fact exists and is affine, smooth, reduced, and irreducible. So this is when start my infatuation with instantons. But okay, we saw a little bit about the instantons on P3, and so the case for rank 2 is closed. These results that I show until now talk a little bit about higher rank of these bundles, but as you can see, always for rank greater or equal 4. So one case is missing, and this one is the one that we're going to talk now, which is the rank 3 case. But why we're going to do that? Because the instanton bundles of rank 2 and second Chern class equal to n, they fulfill irreducible components of the modular space of vector bundles. So studying instanton bundles help us to understand a little bit more about the geometry of the modular space of vector bundles. Okay? So since we're going to talk about rank 3 instanton bundles on P3, I will recall for you the definition of instanton, but just in the case that we're going to use. Okay? So instanton sheaf on P3 is a torsion-free sheaf satisfying these vanishing conditions of the cohomology. Okay? And in this case, it's easy to see that this second Chern class is equal to the charge of the bundle. Okay? And again, if F is locally free, then we are talking about instanton bundles. Okay? Well, but how are we going to study these guys? Our goal here is relate these guys with curves on P3, and for that we're going to use the Hartree-Serre correspondence for vector bundles. So I gave here not the Hartree-Serre correspondence that I believe almost all of you are have seen. So this is the generalization due to Araujo. I'm sorry?
Sorry, but you already mentioned these guys.
In this case, they're going to be Gisger stable. Yes. Not always. In the genetically, I believe so. Because at least for the They are not always, because at least for my case of the orthogonal, for instance, in order to construct the modular space, I have to use GIT. We don't even have how to compute the Giesinger stability on that. Okay. So if X is a smooth algebraic variety and Y is a codimension 2 locally complete intersection subscheme, so when X is P3, this one's going to be a curve. Let these guys be the normal bundle of the subscheme, and L be a line bundle on X, which satisfies this vanish cohomology. So we assume that this guy is generated by R minus 1 global sections, and there exists a rank R vector bundle on X such that this determinant is L, and then F has R minus 1 global sections, whose dependence locus is given by this, and more. If this happens, the vanish cohomology over here, then F is unique up to isomorphism. So we're going to use this a lot, okay? So in our case, X is going to be P3, and this one is going to be a curve. So what happens in our case? First of all, we prove that when you consider a non-degenerate locally complete intersection, a rational curve on P3 of degree n plus 3 with n greater or equal to, then we have the determinant is generated by 2 global sections, and then we have this guy over here corresponding a vector bundle which corresponding to our curve by the Hartree-Serre duality, okay? And this guy over here, this twist of this guy, is going to be an instanton bundle. So we took a curve on P3 by Hartree-Serre correspondence, I mean duality, but it's correspondence, no? By Serre duality correspondence, we have a vector bundle, and this vector bundle has a twisted, which is an instanton bundle. So since I'm going to use this guy, I prefer to call this one the bundle and this one is twisted, but it's just my preference, okay? Well, this is going to be important because we're going to give some spectrum, spectrum, we're going to characterize this vector bundle with given by correspondence by this curve using this spectrum. And also we're going to try to come back given a vector bundle which is instanton and relate with a curve, okay? So we're going to try to do this one-to-one correspondence with these guys. So first of all, let me recall the definition of spectrum, because I don't know if all of you is familiar with. So if I have a rank R torsion for sheaf on P3 with generic splitting type given by this, so this means that these guys respect this order, and let S be this dimension. So there's just a list of any integers also respect this order such that we can compute the dimension of the first and second cohomology groups of these twisted when L respect these and L respect these by these integers that happen on the generically splitting type. So which one with, I don't know if all of you are familiar with computation of cohomology groups. This is a very great tool, would help us a lot. And these guys that appear in here, it's what we call of the spectrum of our sheaf. These guys help us also to classify and try to understand a little bit better of the components of the modular space. And at the beginning it seems to be a little bit strange because we need to ensure this is enough this n over here, but this guy is in fact the second Chern class of our sheaf. So we know how much integers we are talking about, okay? Well, so why I was recalling that? Because if I have a semi-stable, Giesinger semi-stable here, rank 3 vector bundle on P3, and if n is its second Chern class, then F is going to be an instant bundle if and only if we have this spectrum, okay? So you have a little bit of control in how we're going to understand these guys with the spectrum, okay? And also just because we're going to use this later, if I have a rank 3 vector bundle on P3 with Chern classes C1, C2, C3, and if Y its correspondence curve by the Hartree correspondence, then the degree and the arithmetic genus of the curve are related with the Chern classes of our vector bundle. So the invariants of the curve and the invariants of the vector bundle are related, okay? So these result is due to Vogelar, but we also have a different proof of our paper, so I put here just to remember, okay? So this is just a few tools that we're gonna use in a few minutes. So, okay. So now we're trying to come back. Oh, sorry. We're trying to come back. So if I have now a rank 3 instant bundle on P3 with charge n without global sections, and I suppose that if this happen, that means I have at least 2 global sections, then we can write this twisted in this extension where y is a rational curve on P3, okay? So in some way, I now can relate instant bundles with rational curves on P3, and the degree of the curve is related with the charge of my vector bundle, okay?
So this is now the curve corresponding to the bundle by the correspondence?
This one is. So you can, if you start with one, we can construct a curve and vice versa.
So the corresponding curve in this case is rational?
Yes, it's rational. Okay. So, as you can see in here, I ask a little bit. I ask that my vector bundle must have at least 2 global sections. But these guys, for me, at least for instant bundles, are what we call the tooth bundles on P3. So a tooth bundle, it's an instant bundle that it's this cohomology, the dimension of this cohomology it's at least R minus 1, where R is the rank, okay? We can talk about the two bundles like this. So in order to do this correspondence now, and this one-to-one correspondence between instant bundles and the curves on P3, we're going to talk a little bit about the tooth bundles. And at least at the beginning, it seems that we are not talk about all these guys, but in fact, when we took a curve on P3, generated rational smooth curve of degree n plus 3, and we have the bundle which is corresponded by the Hartree correspondence, then it is to see that this guy is in fact not just an instant bundle as we show, but is in toothed bundle. So we're going to be able to do this correspondence properly, okay? And this is also a technical conditions that we're going to use in a minute. So if I take a rational generated smooth curve of degree n plus 3, and if f it's supposed to point in there or there because it's, so its correspondence rank 3 2th bundle of charge n, and then I have these relations between the x2 of the ideal sheaf of the curve and the x2 of my vector bundle, okay? And generic stable rank 3 2th bundle of charge n is a smooth point of the modular space of rank 3 vector bundles of charge classes like this one. So it's instanton, so C1 is 0, it's a vector bundle, so C3 is, and this guy is our charge. So I have this relation between these 2th bundles and our curves, and we have show that these guys is a smooth point on the modular space of vector bundles, okay? So to in fact see that these guys over here, the 2th bundles, it's going to fill a component of the modular space of vector bundles, not only the instantons, but the vector bundles. We're going to use the correspondence between instanton bundles and these curves, and also the Hartree-Fourier correspondence for reflexive sheaves to associate them, okay? So if I took a curve, well, if I took a curve on P3, which satisfies the Hartree-Fourier correspondence, then I have a rank 3 coherent sheaf on P3, and I have this, that F is a vector bundle, that one of my first result, if and only if this guy is on an extension of E, where E is a rank 2 reflexive sheaf, which also corresponds with Y via Hartree-Fourier correspondence. So that's one I believe that almost all of you is familiar with, that one from Hartree paper. So I have a curve. I can relate this curve with a rank 3 vector bundle if and only if I also have that this guy is an extension of a rank 2 reflexive sheaf, okay? And these two guys, the bundle and the reflexive sheaf, are both related with the same curve via the Hartree-Fourier correspondence. So this is going to be very useful for us because we're going to try to understand the modular space of these guys using the modular space of these guys over here, okay? So for general charge, it's a little bit difficult. For charge equals 1, Jardim and Gargatti already have done some studies of it. So we are going to focus on charge 2 case, okay? So we have a one-to-one correspondence between our charge 2 rank 3 stable instanton bundles on P3 and sigma a global section of this guy, this one related with the curve via Hartree-Fourier correspondence, and pairs of normalized rank 2 stable reflexive sheaves on P3, which are in classes -1, 3, and 3. And these extensions over here, and this 3 is supposed to be OP3, okay? So if we take a charge 2 rank 3 stable instanton bundle on P3, we can relate with a normalized rank 2 stable reflexive sheaf on P3, and these two guys are related with the same curve on P3, okay? So why this is important? Because we're going to build the modular space of the stable rank 3 instanton bundles, use the modular space of these guys, which are already being studied by Chen. Okay? Okay. So our goal is to prove that the the family of instanton bundles of rank 3, of charge 2, and P3 fulfill a reducible component of the modular space of rank 3 stable vector bundles on P3. Okay? So what we're going to do is let R be the modular space of stable rank 2 reflexive sheaves with Charn classes equals to -1, 3, and 3. Let this guy be its corresponding universal bundle. Okay? Chang proved that this modular space is the rational variety of dimension 19. And if we consider the projection into the second coordinate, for each reflexive sheaf over here, the base change theorem gives us this, that these extensions over here are isomorphic to these extensions and to these cohomologies over here. And with a little help of our friends, we can compute these vanishes over here. Okay? So I really try to obey Araujo and not to be very technical, but at this point, I don't know, I can see how I cannot do this to all of you, so I'm sorry. But this, we can prove this vanishing, so I think you can believe in me now. So what we're going to do now is use the local to global spectral sequence of X shifts, and then we can compute. I don't know why I can go. Oh, okay. So this X over here, first X, is isomorphic to this guy, and then this dimension is 3. So this guy is, which is the image of this guy over here, is a reducible variety of dimension 22, 19, plus 3, that parametrizes our pairs of vector bundles, reflexive sheaves in this guy. So what of these resumes is that we can now consider this map given by from this guy, okay, to the modular space of vector bundles of charge 0 to, for Charn class 0 to 0, given by the composition of the one-to-one correspondence and the projection on the first coordinate. So this guy, we can show the factorized by this one, and more. For every vector bundle, instanton bundle, over here, we have that this dimension is in fact 6. So this guy, given by our constructor, is surjective, open morphism of relative dimension 6, which implies that this happen and is a reducible variety of dimension 16, 22 minus 6. And we have our result. So the family of stable rank 3 instanton bundles of charge 2 is reducible and has dimension 16. Okay? So now we're going to prove that this guy is in fact the whole modular space of vector bundles of Charn class 0 to 0. Okay? So every rank 3 stable vector bundle on P3 of Charn class 0 to 0 is an instanton bundle. So let F be a rank 3 stable vector bundle on P3 of these Charn classes. So since I have Charn class second Charn equals to 2, then this is a spectrum from my guy. Okay? Well, by the properties of the spectrum that I gave in the theorem that defines this spectrum, we have two possibilities to cover. So my spectrum is 0, 0, or my spectrum is this one. If my spectrum is the first one, then I have my guy is instanton bundle by the lemma that I gave before, so it's okay. And so let's prove that this cannot happen, okay? So in fact, when you try to compute these dimensions of these cohomology groups, we have that this guy and this guy is equals to 1, and this guy is equals to 0. By the Heisenberg-Riemann-Roch formula, we have that the Euler characteristic of this guy is 6. So this dimension must be greater or equal to 6. And there is this locally complete intersection rational quintic in P3 by our correspondence that corresponds to this guy by the Hartree-Serre correspondence. So F is an instant bundle of charge 2, hence this must happen, which contradicts this over here. So this spectral cannot happen, so our rank 3 stable vector bundle is in fact an instant bundle. And with this, we have that the modular space of rank 3 stable vector bundles, which are in classes equals to 0 to 0, is irreducible, generically smooth of dimension 16. So by our previous result, we proved that this happened. This is irreducible of dimension 16. And if F is an instant bundle, be a generic toothed instant bundle, we saw that this vanish happened. This is one of the lemmas that I showed you before. And additionally, we have the dimension of this x1 is 16, which coincides with the dimension that we compute for this guy. This implies that the generic toothed instant bundle is a smooth point of our modular space, okay? So with this, we prove that, in fact, these guys, these toothed bundles, the instant bundles, they fulfill one component, and that we have the smoothness and the generic smoothness and the reducibility of these guys. So this is some of the reference that I use, and thank you so much.
Okay, question.